So, in a nutshell, tonight we're going to see and go beyond our universe. In the next few minutes, we're going to show and tell all we can see, all we can say about what fact does lie beyond. All of it. In a nutshell, and that's Ian, if you want. Why? Because we need this knowledge to define two important terms that have a big and immediate impact on all of us. Term number one, infinity. Term number two, boundaries, also known as limits. As far as all we can see, looking from planet Earth, you walk right outside here, we're clear, and you'd all recognize this. It's the Milky Way galaxy in which we live, our home galaxy, the Milky Way. Now, where we're going tonight, not only beyond our Milky Way, beyond our own universe. First stop in this journey is these two nebulae, known as the Large and Small Magellan Clouds, and they're just satellite galaxies, really little baby galaxies that orbit the Milky Way. Now, looking about 10, 13 times further, this is the first big Milky Way-sized galaxy that we come to. In fact, it's our sister galaxy, Andromeda. Really, this galaxy and our own Milky Way are kind of a pair, and it's believed that, in fact, if we were there looking back, this is what we would see of us. This is a big galaxy. Now, there's Andromeda's companion galaxy, much smaller object, but not much further away. And that is basically all we can see, all of it, in a nutshell, with our unaided human vision. All right, so let's skip forward to what we can see with the world's best telescopes, or the best telescopes out of this world, because this is the view from NASA's Hubble Space Telescope. This is, in fact, Hubble Ultra Deep Field. It is the longest exposure photograph ever taken, hundreds of hours. It's the deepest view ever shown, and to date, of really how much we can see at the visible limits of our universe. In fact, we're going to zoom in, and I'll show you as we go 10x, and zoom in toward this little red dot here, and then 100x, you can see in this picture the limits of our visible universe. Because what you're seeing in the center, that ERO, it's an extended red object. The point is, it's not a point, it's not a star, that's a galaxy. That galaxy is receding from our Earth, our own Milky Way, at 96% the speed of light. If you look beyond this, what you get is basically nothing, an inky blackness. Now, I know you see some noise and pixelation, that's really a product, an artifact of the system that they're using, but believe me, beyond that is nothing. They call it, in fact, there's a term astronomers use for this, the cosmic dark ages. I don't want to get too technical, but I do want to point out, I promise we show all we can see, that's it, as of tonight, until the next generation of telescope. As far as all we can see, this is a little bit easier, all we can say, because in fact, all that is known about, well, everything beyond our own galaxy, that is everything extragalactic, is all research from the astronomical journals, the papers and the data that are collected. They're all assembled in one single place, known as the NASA IPAC Extragalactic Database. What I do with the Fornet, the part I help work on, is I basically keep track of the galaxy distance estimates. I make a tabulation database of the published estimates of the distances to these galaxies. It's basically a small subset of this database we call NED-D for distances, galaxy distances. So these distances are big difference makers in the field of extragalactic astronomy. I swear to gosh, they are the data that are lifting extragalactic astronomy. I mean, one distance at a time, transforming the field from a science of apparent measurements. You know, you've got the apparent positions on the sky, the apparent diameters, their apparent magnitudes. No. With a distance added to that, you transform these apparent properties into the absolute diameter of the object, into its absolute position, not only in 2 dimensions on the sphere, but in 3 dimensions of space, including depth and distance. These distance estimates are the stepping stones, the milepost mile markers, if you will. They're the only thing that we have to measure the exact size of our universe. Really what's important to us tonight in our idea is not the fact that it's 14.1 billion year old universe or 14.23 as some might argue. It's the fact that it's anything. I mean anything at all. I mean if it's X, then it begs the question, what comes after Y? I just want to again get to the definitions of infinity and boundaries, and we're kind of at that tipping point now, because beyond our own universe, 14 billion years, what comes after that? And I think you'd be surprised at how limited the possibilities are. In fact, beyond our universe, one, there is A, nothing, or B, something. I don't think I've left anything out. So I've got almost everybody up to beyond our universe. One, there is B, something. So by a show of hands, I'd like to see now what that something is in our collective opinions. There is A, something completely different. Who thinks it's completely different? We'll never understand it. Got some takers. Okay, a little more division here. And who thinks B is just more of the same? More matter, more energy, just goes on and on and on. In a nutshell, our universe is really 14 billion light years across, just one of a whole slew of universes, all side by side, going on, onward, and infinitum, infinitely to the left, infinitely to the right, infinitely up, infinitely down, infinitely forward, infinitely back. Just a pile of universes. In fact, that pile makes it look kind of like atoms. I mean, this is exactly what a bunch of atoms of atomic angstrom diameters would look like. Infinity is, we normally think of it, 3 dimensions. Yeah, these universes, all the same size, go onward infinitely. To the left, the right, front, back, up, down. What we're talking about is a somewhat broader definition, because they go upward in size to larger and larger scales. And then a third definition, they go downward in size, inward, smaller and smaller scales. So that's a little bit more about infinity. So we have big boundaries, universes, and little boundaries, atoms. The main point is, it's just a recurring pattern. It's basically a fractal. This isn't rocket science. Fractal patterns occur on the beaches and trees and plants. You see them everywhere, and it would, if anything, be surprising if the universe didn't work this way. You're simply seeing a pattern repeat itself over and over and over again in size. It's just a size difference. It goes from atoms at the small size to universes at the big size.